So let's just get started with the recursion. So okay, so before we dive deeper into recursion, let's first understand what recursion is. So I think some of you might be a little bit familiar with it. So what exactly is recursion basically? So if I ask you, the common, at least the answer that I get is recursion is basically a function calling itself. So we define recursion as a function calling itself. Yes, it's obviously correct to an extent, but why do you think a function will actually call itself? What's the need? What's the need for a function that it is going to call itself? So okay, so we write a function actually in order to solve a problem. So let's not think it programmatically. Okay, let's just think that we have a problem in hand and we have to solve that problem. So a function calling itself basically would mean that the solution that I have to figure out of a problem actually depends on solution to a smaller problem, but which is exactly of the same nature. So I have to solve the problem and the problem with the same approach, but now this time the difference is that the problem is a smaller version of the original problem that I actually have to solve. So what we are working over is we are solving a problem with a smaller version of it. Okay, so let's not get into words. I'll just quickly move over to an example to help you understand better. Let's say a very simple problem that I have to solve is actually factorial. So I have to calculate factorial of a number. So you are given a number and you have to calculate this factorial. Let's take the number to be 4. So let's say I have to calculate 4 factorial. So I can write 4 factorial like this, right? 4 factorial calculate, if I have to calculate it, it's 4 cross 3 cross 2 cross 1. So that is how we calculate 4 factorial. Okay. So if we talk about this product portion, I can actually write it like this. So 4 factorial calculate, if I have to calculate it, I can write it as 4 into 3 factorial. So which means if I have answer to 3 factorial, I will be able to calculate 4 factorial. If I have the answer of 3 factorial ready with me, I should be find out 4 factorial. That is, I just have to multiply it with 4 and I will have answer with me, right? So now our original problem was to calculate 4 factorial, and now by writing this, what I am doing is I am saying the solution to my original problem, which was obviously bigger in size, actually depends on solution to a problem which is of same nature. So same nature means the approach that I will use to find out 4 factorial, in a similar approach I will be able to figure out 3 factorial as well. So I am solving a problem of same nature, but this time the problem is smaller. So 3 factorial, calculating 3 factorial is obviously smaller than calculating 4 factorial. So the problem that I am trying to solve is of smaller nature now. So if I just further and figure out how are we going to calculate 3 factorial, I can actually write it like this. So if I have to calculate 3 factorial, I can write it as 3 cross 2 factorial. So which means if I will have 2 factorial with me, I should be able to figure out 3 factorial as well. I just have to multiply the answer of 2 factorial with 3. So okay, so now for 3 factorial we are done. For 2 factorial, I can write it like this. I can write 2 factorial as 2 cross 1 factorial. So we should be able to figure that out. Okay, let's just generalize this and write it for n. So I have to calculate n factorial, and now I can write it like this. So n factorial is n cross n minus 1 factorial. So this is the logic. So if I have the answer of n minus 1 factorial, I will be able to calculate n factorial. So okay, so now we are clear with the logic. So let's just convert it into a function. So let me write a function. I'll just write it here first. So let me write a function, that is, I have to calculate factorial n. So function to figure out n factorial. If I have to find n factorial, what I should have is, I should first have answer of n minus 1 factorial. Let's say I need answer of n minus 1 factorial. So to find out n minus 1 factorial, I'll actually use the same function. So this was the function, right? The job of the function is to calculate factorial for any number. So if the target is to find out factorial for n, if I say, hey, find out the factorial for n minus 1, it should be able to solve. So what I am doing is I am writing that factorial n minus 1 is my requirement. So once I have this, I should be able to figure out the final answer, that is n multiplied by the small answer. What was the small answer? Small answer was factorial of n minus 1. So exactly same logic that we thought of, I am just writing the code for it. This was the logic we thought of, now we are done with the code. Okay. So which means, agar mujhe 4 factorial, if I have to calculate 4 factorial, I would need 3 factorial. Now 3 factorial will say, if you have to find out 3 factorial, you need to figure out 2 factorial. So, okay, now I have 2 factorial with me. So 2 factorial will say, in order to figure out 2 factorial, you need answer of 1 factorial. Okay, so I need answer of 1 factorial. I can write 1 factorial like this. So in order to figure out 1 factorial, I need answer of 0 factorial. 0 will say I need answer of minus 1, minus 1 will say answer of minus 2. We know that factorials are not there for negative numbers, but the code that we have written, I think the process will continue. N is saying I need to have n minus 1's answer. So n minus 1 will say, and I need to have n minus 2's answer, and this will continue, right? So if I just write this code and try to run it, this will continue. This is not going to stop because we are not stopping it. See, our intention is actually to divide the problem, keep on breaking the problem, diluting the problem at every step, so that we are able to achieve its answer. So what we are doing is, at every step, we started with 4, we are actually breaking down our problem. We went to 3, we went to 2, we went to 1, we went to 0. Now the 0 is actually a point where my problem is pretty simple now. So 0 factorial is obvious. I don't need to write any big factorial code or use recursion and anything to figure out. It's pretty simple. I have divided my problem and I've reached at a point which is very simple to figure out. So that is exactly my point where I should stop. This is my ending point or stopping point where I have to stop. So some stage down the line I need to stop, or you can think of that a very simple problem whose answer I know just straight away. I don't have to do anything to figure that out. Now that simplest position or point, we call it as a base case. Why do I need it? I actually need to stop this calling process somewhere. So what I missed here is, I have missed actually adding a base case here. So what will be my base case? Simplest case that I have to solve is, if somebody asks me, hey, figure out the answer of 0 factorial. So I know that. So what I should do is, I should just return 1 here. That this is the answer, which is simple, and I know. I don't have to put my brain in figuring out its solution. So this is done. So this is actually the simplest problem that I have to solve, and we call this simplest problem as base case. Okay, so we have framed our solution here. Let's just do one thing. Let's move to the code and write the code for it. Okay, so I have this main with me. What I am supposed to do is, I have to write function for factorial. Return type would be an integer. Fact is the name of the function. N is the argument. So this is the factorial function that I have to write. So the first thing that we should write here is the base case. So base case we decided that it's n equal to 0 because that's the simplest factorial problem anybody can give you. So 0 factorial is pretty easy to solve. So the answer of 0 factorial is 1. If the number is not 0, then I'll use recursion to solve it. So what we should do is, we should calculate small answer to the smaller problem. What is the smaller problem? The smaller problem over here is n minus 1 factorial. So I should figure out answer to it. And once I have answer to the smaller problem, I should be able to return it. So with this, I think we are done with the function. Let's just do one thing. Let's quickly test it. So I am just testing it for n4 once. Okay, so let's compile our code and run it. So answer of n factorial, so 4 factorial is 24. Okay, let's just go back to the code, test it with another value of n. So answer of 5 factorial is 120. So which means that our code is working fine. I'll just go back to it. Okay, so now we have seen, we have written the code for it, we have tested it for value or 2, and we have figured out it's working fine. So let's quickly understand what is actually happening inside it. How are these recursion or the calls that we know are working? Okay, so we know that whatever code we execute starts with the main. So now I have started with the main. So inside main you have an integer n whose value is 5, right? This is what I have. I have a main and an integer n whose value is 5. So inside main at line number 17 we have called a function factorial. So this will call factorial and with the value of n as 5. This is the function call that will take place. So factorial of 5. So this is happening. Let's get into this function call at line number 5. So inside the function we'll move to line number 7. We'll check if n is equal to 0. So is 5 equal to 0? No. So if it is not, I'll move to line number 10, and at line number 10 I need to have answer of factorial n minus 1. So there is another function called taking place. The call that is taking place is to the same function but with a different input. So the call that will take place is factorial of 4. This is the call that will take place. So we will call factorial of 4. Okay. So for 4 factorial, now we will start with the same process. Factorial 4 is a completely new function in itself. We will start here. The value of n here was 5. The value of n for factorial 4 will be 4. We will again dive into the function, start with line number 5. Now n is 4 this time. Next I'll come up to line number 7. I'll check if 4 is equal to 0. No, 4 is not equal to 0. I'll move to line number 10 and this time I need small answer, factorial n minus 1. N for this call was 4, so n minus 1 will be 3. So I'll call factorial 3 with n as 3. So once we have called factorial 3, we'll again start with line number 5. N is 3 now. Check if 3 is 0. No, it is not. Factorial 3 will say I need answer of factorial 2 first. So we will have to stop and we'll have to move to factorial of 2 with n value 2. So factorial 2, again the same procedure will take place. 2 is not equal to 0. So I'll come over to line number 10. Now factorial 2 will say I need answer of factorial 1 first. So code for factorial 2 will stop here and we will start execution for factorial 1. I hope all of you are clear with the concepts of functions. So whenever one function calls another function, the execution for the calling function stops there and we directly move on to the function that is called. So, okay, so we were into factorial 1 with n is equal to 1. Now 1 is not equal to 0. We will come up and we will make a call to factorial of 0. For factorial of 0, we will proceed to the function. Now at line number 7, the condition, our base case will match. So n is 0, so we will return 1 this time. So factorial 0 now has its answer ready and it will return its answer. Okay. So these were the calls that were taking place. So whatever calls, function calls that we do, that we make, obviously system has to store it somewhere. They must be stored somewhere. So they are stored in a memory portion called stack. So all the calls that you make are actually stored in a memory portion called stack. I am just drawing this stack memory here. What happens in stack memory? You don't have to think too much about it. It's just that I store some information about the function inside the stack. So सबसे पहले if I am into main, I store some information about main. What is that information? Basically the line number at which I have to return and the variables of main. I basically store that information here. So the first function that was called originally, this is 1, this is 2, this is 3, this is 4, this is 5, 6 and 7. Just the order of calls that happened. So the first function that was called was main. So I have a main here. Main has its n whose value is 5. Next main called factorial of 5. So the next call was factorial of 5 with n as 4. The next call factorial 4. Sorry, this is 5 factorial 4. I will quickly write all of them. Factorial 2, n value 2, factorial 1, n value 1 and factorial 0, n value 0. So this is how the calls took place. This was call number 1, call number 2, call number 3, 4, 5, 6 and 7. I have just drawn these calls into a stack here. So they are same. The calls are exactly same. Okay. So we were to a point that main called factorial 5. Factorial 5 will call factorial 4. 4 will call 3, 2, 1, 0. And all these calls will be put up into a stack. The first call main, I have put it into stack. The second call was 5, I have put it into 5. The 4, 3, 2, 1. Similarly, I have placed all calls here inside the stack. Now, all these calls are actually waiting for the answer from the function that it has called. That is, main is there inside the stack and it is waiting for answer of 5 factorial. Factorial 5 is there inside the stack and is waiting for the answer of 4 factorial. 4 is waiting for the answer of 3, 3 is waiting for answer of 2, 1 and 0. Okay, so 0 ke liye, let's just look at the code. N equal to 0, we returned 1. So that means 0 factorial will return answer 1. Now to whom will 0 factorial return its answer? 0 factorial will return its answer to the function that has called it. So which function called 0 factorial? Factorial 1 actually called 0 factorial. So factorial 0 will return its answer to factorial 1 and not mean. So many times I find students getting confused here. So you need to be sure that whatever answer a function is returning is, it is returning to its callee. So factorial 0 was called by factorial 1, so it will return its answer to factorial 1. Okay. So factorial 0 will return answer, that is 1, to factorial 1. So whenever a function returns its answer, so it's no more required in the stack, so its data from the stack is actually deleted. So it has returned answer to factorial 1. Now factorial 1 was waiting at this line number 10 for answer of, so I have just inserted a space. So factorial 1 was waiting for the answer at line number 11. So small answer for factorial 1 would be 1. So it will calculate its factorial now, n into small answer, 1 into 1, it will return 1. It will return 1 to function factorial 2. So it will return its answer to this function. So small answer, if I have to write, for factorial 2 would be 1. Factorial 2 has its small answer, it will calculate its factorial, that is 2, and return to factorial of 3. So small answer, I am just writing essay here, small answer for factorial 3 would be answer from factorial 2, that is 2. So it will perform n into 2, that is 6, and return answer here. Now small answer for n is equal to 4 would be 6. Now it will calculate 4 into 6, that is 24, and return here. All these calls, when they are done, whenever you return a function, these calls will be deleted from the memory where I have stored them. So as soon as factorial 4 returns, its call is done and we'll remove it. Factorial 5 is still there in memory because it is waiting for the result. Mean is still there in memory because it is waiting for the result. So factorial 5, small answer for factorial 5 will be 24. So factorial of 5, it will calculate its answer, that is 5 cross 24 and 120, and now factorial 5 is going to return its result to mean. Mean was the function which called factorial 5, so factorial 5 is going to return its answer to mean. So at mean, what we did was we just recovered our answer here and we printed it. So I'll print the result, that is 120, and after printing the result, even mean is gone. So this is how actually the flow of events or the flow of function calls that we are making is working. Now one thing that you should be definitely clear about is all these function calls that I am making are completely different from one another. They are completely different. What is common is just the name, just the function that we are using here in all these calls. So all these function calls are completely separate. They have their own variables. That means the variable n, which takes 4 bytes, is actually local to main. Similarly, factorial 5 will have its own n, that is taking some storage. Factorial 4 will have its own n, 3 will have its own n, and so on. So different n values, different small answer values for different functions. So it's just that the function that we are calling ends up to be same, but that doesn't mean that everything is happening there. These are separate function calls. In order to get a clarity, you can visualize that this code, this portion of code, line number 6 to 13, is there with every function call. So every function call has its own code which it is executing, which it knows where to start from. Every function call has its own variables. So if you change n for one call, it is not going to change for all other calls. Whatever values of n they are local to the function. It's just local to one function and it is not common for all the function calls. And even this value of small answer is a variable that is local to every factorial call that you are making. They are not shared by all factorial calls. So this is the flow, how we proceed, and I assume you should be clear about that. So in case you have any doubts till whatever we have studied, you can put them into comments. Okay, so I hope we have dived into all the details about factorial and we are clear with it. Okay, so let me just clear this up. Okay, so let me just come back to code over here. So at this portion of code, we wrote a line that we need answer of fact n minus 1, and while our logic, writing our code and our computations, we assumed that we'll get its answer, right? We didn't think about actually all this stuff and all this part. We didn't dive into how the work flows, and actually this is how you should solve a recursion problem. You should think solving a recursion problem broadly without actually diving deeper into the details. Okay, this function must have called the another function and the procedure must have gone. So you don't have to think that deeper. You just should think broadly. I would say I have a problem of factorial in my mind. I need to figure out, now to solve factorial n, I need n minus 1, and that's exactly the way we did, the way we started. I just need answer of factorial n minus 1. So I wrote factorial n minus 1 over here, and I assumed that I'll get its answer correctly, and I multiplied the result and returned it back. So now this assumption that I'll get its answer correctly is actually something big, right? How are you assuming this is working fine? So you don't have to doubt it, because the concept of recursion that we are studying has actually its root inside a very important mathematical concept. I am sure all of you must have gone through it. It's principle of mathematical induction, PMI. So I am sure all of you must have been through it. So the concept of PMI basically, so okay, so what PMI was, so let me just clear this up. Okay, so PMI basically was, so if I have to prove, let's say, a formula, so what we used to do is, if I have to prove a formula for any natural number, for all natural numbers, so what we used to do is, let's say the formula is sum of first n natural numbers. So this is n into n plus 1 by 2, right? So what we used to do it, we used to test it for a very small value, let's say for n is equal to 0, and see if it is working for n is equal to 0. It is working fine. Then next step was induction hypothesis. So we used to make a hypothesis, that is the formula will work well for a natural number k. So this was our induction hypothesis, right? This was our induction hypothesis that we used to do. So this is our induction hypothesis. So using this hypothesis, we have to prove that the formula is fine for f of k plus 1. These were the steps that we were following for recursion, and if we are able to prove that the formula is fine for f of k plus 1, we used to say that the formula will work for any natural number, right? What we did, we took an hypothesis, we tested for a small value, we took an hypothesis, we moved to induction step where I actually have to prove it for k plus 1, and once I am able to solve my induction step correctly, I can say that it is going to work for any natural number. Now this is a big statement, right? You have just tested it for k, you have just assumed for k, proved it for k plus 1, and now you are saying that it will work for any natural number. So how do you think PMI, through PMI we are able to achieve that? Is there a magic or somewhat or assumption that we are taking? So no. So basically what we have achieved here is, if I know f of k's answer, I am able to figure out f of k plus 1's answer, right? So if I know that sum of first 0 natural number is 0, I should be able to calculate sum of first 1 natural numbers. I just have to write this 1 plus sum of first 0 natural numbers. Similarly, if I have to figure out sum of first 2 natural numbers, I should be able to write it like this. Now when I was calculating f1, I know f0 is 2. So here f0 is 2, I have proved it for fk plus 1. So I can assume f of 1 will also work, because I have just proved it. I have just taught induction how to take a step using fk, moving on to fk plus 1. So if f of 0 is true, I can say f of 1 is 2. Now to calculate f of 2, I needed f of 1. Now I know f of 1 is figured out correctly. I can say f of 2 is fine. Similarly, I can test it for any value of k, and it will work for all values of integers, all values of natural numbers from that. So basically PMI is no assumption, but valid logic is running behind it, right? Similarly, if we look at our recursive code from the perspective of PMI, I am sure you will be able to relate it. So if I just come here, okay. So we had a basic step about which we were sure. So this basically, the basic step that we were sure about is our base case, if I have to relate it. And then we took a induction hypothesis that f of k is fine, right? Similarly, similar to the hypothesis, we assumed here that factorial n minus 1 will work fine, similar to our hypothesis step. Then we used to do it for f of k plus 1. So we don't have to prove anything, but yes, we can take that assumption forward and assume that I'll get answer of factorial of n, assuming that factorial of n minus 1 is figured out correctly. So the roots of recursion are actually into PMI concepts. So if we are able to grasp PMI, we should be able to understand recursion well and structure our code properly. So that's how our code is structured, assuming that I have answer to a very simple problem, assuming that I know how to take a step. I am assuming that f of n minus 1 will work, and then I just have to calculate answer of f of n. So this is basically for recursion. Okay. So we are actually done with this part. So whenever you guys are solving any recursion problem, I think there are 3 important steps similar to these 3 steps that we have in PMI that we should take care about. If I look at the structure of my recursive code, the first step that I have to write down and I have to think about is my base case. So the first and the very important step that I should be concerned about is the base case. And whenever you have to think about base case, you don't have to complicate yourself. Just think what can be the simplest problem that anybody can give you in this regard. So the simplest factorial problem that I have in my hand is factorial 0. That's why I chose my base case here. Okay, so the next step is you need to decide what does the smaller problem mean for you. So in this case, the smaller problem for me was, if I have to calculate factorial n, then I need answer of n minus 1. So the smaller problem was, if I have n, I should be able to figure out n minus 1. I need answer of n minus 1. This is the smaller problem, but this will not be the case every time. Every time you don't have to move from n to n minus 1. Or in some cases of recursion, there may be more than one smaller problems whose answer you want. So you should be clear what does a smaller problem mean for you and how are you actually going to break that step down. So in this case, I was doing n minus 1. In other cases, it may be different depending on the problem in hand. So, and the third step was, so you have small answer, you have base case, you are done with it. Now you need to do some calculation work around it, small answer calculation part, in order to achieve that target. So the calculation part that I was doing there was this multiplication part. Now I need to be sure that this part is correct, right? If I'll make mistake in any one of the 3 steps, my code will not be correct, and you can't then take that assumption that recursion will work fine. So you should be clear that while writing code, you are focused on these 3 steps. Generally, all recursive codes have just these 3 steps that you should be careful about. The base case, figuring out what a smaller problem is, calling recursion to solve that smaller problem. You don't have to worry about factorial n minus 1. Recursion will do that for you. You can straight away assume that this will work fine. And the last step was performing calculations around it in order to achieve the final answer. So if all these 3 stages, all these 3 steps are done completely, you are good to go. Your function will work fine. Okay, so let's just, we are done with enough of this factorial. Let's quickly take another example and move forward with another example so that we grasp recursion better. So let me just clear this up. Okay, so the next problem that we will discuss is, we have this with us, the next problem that we will discuss is to calculate power of a number recursively. So what you have to do is, you just have to figure out x to the power n. So x and n will be provided to you by the user. You will know what the value of x and n is, and you have to calculate x to the power n and return the result. Okay, so I'll assume the power will be positive for now. So if I have to calculate x to the power n, I think we should just think and figure out how are we going to do it. So let's say, let's just simplify it. I have to calculate 4 to the power 3. So can I write 4 to the power 3 like this? So 4 cross 4 to the power 2, and if I have answer of 4 to the power 2, I should be able to calculate 4 to the power 3. Similarly, if I have to calculate, let's say 5 to the power 10, so if I have to solve it, what we should do is, I can write it as 5 cross 5 to the power 9. So if I have answer of 5 to the power 9, I should be able to calculate answer of 5 to the power 10 as well. So this is our logic. For x to the power n, let's just generalize it. I can write it like this. So x cross x to the power of n minus 1. I can just write it like this. Okay. So let's try and write code for the same. So if I have to write it, we need to return the answer. I'll call my function power. So what I have to do is, I need x, I need n in order to calculate power. So I need these 2 values in order to figure out the answer. Okay. So the first step in our recursion solution should be the base step. Base case should be, what should be the simplest power problem that you don't have to put up your brain to. So one thing that we know is, x to the power of 0 is 1 definitely for any value of x, right? So this should be my base case. If power is n, if power is 0, then I don't have to do any calculations, any computations. I straight away know my answer. So if n is equal to 0, the result should be that x to the power 0 is 1. So I know x to the power 0 is 1. Now in order to solve x to the power n, what I need is answer of x to the power of n minus 1. So my small answer that I need is x to the power of n minus 1. Now I just wrote this power function whose task is to perform x to the power of n. Now I need x to the power of n minus 1. Same problem, right, with just a smaller power. So I'll use the same function power to figure out x to the power of n minus 1. Okay, and I can simply return this. So, if I have to calculate x to the power of n, I need x to the power of n minus 1, and we will trust recursion and assume that power x to the power n minus 1 will work fine. I just need to be careful about that my base case is fine, my calculation part is correct, the recursion will do its way. Okay. So, let us just run it. Let us say we take a smaller value. X is 4, n is 3. Now, I do not need factorial, I need power and x comma n. Let us just run it. Okay, we just missed a semicolon. Let me add it. So, I just missed a semicolon at line number 24. Okay, so 4 to the power 3 is 64, so which is the correct answer, which means our code is working well. Okay. So, in order to solve a recursion problem, again while writing code I am emphasizing this part very strictly. While writing code, you should not think how x to the power n minus 1 is going to compute. You should not worry about that. You should just straight away write and assume that I will get its answer. I have x to the power of n minus 1 here with me, and with this answer I am just using it. Okay. So, Ashwini is asking, can't we directly return? There isn't a problem, Ashwini. I just took small answer to just emphasize on the step that I need the answer of the smaller problem first. We can directly return. There isn't a problem there. Okay. So let's just come back to power. And we will test the working of power. Quickly dry run it. See why I am doing it, because ultimately all of us should understand how recursion works. But if we will think too deep while writing code, we will not be able to write it. We will just get stuck at that point, and many of us face this problem. So, we should not think about it at the time we are writing code. At the time we are writing code, we should just worry about the steps, the procedure that we are following, and after that you have tested, you have tried your code that is working fine, you should definitely dry run it and grasp how things are working. So, I will not dive too much into it, but I will quickly write the function calls. So, for the first step I have main. Main has its own x and n. X is 4, n is 3. Now, main is going to call power function with arguments 4, 3, and now n is 3. So, 3 is not equal to 0. I will calculate, I would need small answer. So, in order to solve one small answer, I need to call power of 4, 2. So, now the same procedure will be followed for the function call 4, 2, and for 4, 2, n is 2, this is x, this is n. So, n is not 0, so I need to move further, and I need answer of 4, 1. For 4, 1, x is 4, n is 1. Again 1 is not 0, I will move further and call power of 4, 0. So, in order to find 4, 0, now x is 4, n is 0. Now, my base case will fit in. So, for any number to the power 0 is 1. So, I will straight away return 1. I will just return 1. This 1 will be returned to which function? To the function that called it, and the function that called it is power 1. So, 1 will be returned to power 1. It will return 1 to power 1. Now, power 1 is waiting for answer from power 0. So power 0 has just returned its answer. So small answer now is 1. What power 1 will do? Power 1 will solve x into small answer. So x into small answer is 4 into 1. It will return 1. Power 4 comma 2 now has its small answer as it will return 4, sorry. Power 4 comma 2 will now have its small answer as 4. What it will do is multiply x with small answer. So x is 4, 4 cross 4 is 16. It will return 16. Power 4 comma 3's small answer is now 16. It will multiply x with 16 and return the answer, that is 64, to main. Main will finally print it and we are done. So these are the steps that we are following. So these are the procedures that we follow. I hope you have understood what were the steps followed, how you should approach a problem, how you should proceed around it, and move further and write code for it. Okay, so now I hope you guys are okay with the power function, and so we have done factorial, we have done power function, two relatively easier problems to get a hold of recursion, to get a hold of how flow work. And again I am emphasizing, please consider all these function calls as separate. They are not same. It's just that they happen to share the same code, the same name, because the function is solving the same problem. But yes, the function calls are completely separate. They all have their own variables and own storages. Okay. So after factorial and power, let's move to another problem. I am sure many of you must have heard about it. That is Tower of Hanoi. So let's discuss Tower of Hanoi now. Let me just clear this up. Okay, and I'll straight away move to Tower of Hanoi. Okay, so before moving on to everything, let's first understand what actually Tower of Hanoi is. So Tower of Hanoi problem says that you have 3 rods with you, and I'll call them A, B, C, and rod A has a certain number of discs in it. So there are certain number of discs inside rod A. So what we have to do is, okay, so let's say I have these 3 discs, disk number 1, 2 and 3. What we have to do is transfer all these discs from rod A to C. A is my source, the start, D is my destination, where I have to put all these rods ultimately. B is just a helper with me, helper rod that I can use in my procedure. So what I have to do is I have to transfer all these rods from A to B. Now these rods are of different sizes. At the last should be the rod of maximum size. So 3 is the biggest of all, then 2, then 1. So we have placed them in this manner, and we have to transfer all of them straight away from A to C, and we need to maintain their order. So maintaining the order of the discs, we have to transfer them from A to C. Okay, so there are some constraints around it. First constraint is obviously that you have to transfer all the discs in the same order from A to C. That means the target should be this 1, 2, 3. Now one thing that I have to do is I can move only one plate at a time. So I have to move only one disc at a time, and I cannot place a disc of bigger size over a disc of smaller size, which means this is incorrect. You cannot do this. This is not allowed. So you cannot place a disk of bigger size over a disk of smaller size. So you should not do that. So these are the constraints. So depending on this, following all the constraints, we have to transfer all these disks from A to C. Okay. So before thinking about the code and any other stuff, A, B, C, let's say I just have one disk with me. N is number of disks. So if N is 1, then what I actually have to do? So if N is 1, I think it is pretty much simple for you. You don't have to do much around it. So if N is 1, what you can do is directly take this disk from A and place it at C. So you just have to do this. Take a disk from A, place it over C. Okay. So this was pretty simple. Let's say this will be removed then. N is 2. So rod A, rod B, rod C, number of disks are 2 this time. This is 1, this is 2. So if I have to transfer all the disks from A to C, what should I do is, first of all, the first step I should do is, I should move plate 1 and move disk 1 and put it to B. So what I should do is move 1 from A to B. That means remove 1 from A, put it at B. Okay. So 1 is at B. Now what I should do is, next thing that I need to do is, this is my target configuration, right? The target that I have to achieve. This is my target configuration. So what I should next do is, I should simply move 2 from A to C. I can do that. So let's do this. Move 2 from A to C. So I have 2 here. I think all of you must have got it. The last step would be moving 1 from B to C. So what I should do is move 1 from B to C. C was my destination and I have achieved the configuration. These were the 3 steps that I have to follow, right? For 2 it is pretty simple. So n is equal to 2 was okay, n is equal to 1 was okay, n is equal to 3, 4, 5. I think the number of steps will increase and it will get a bit difficult for us to proceed. Okay. So for n is equal to 3 even, I will just erase this up. Let's say I will just erase this value of n, and if I say I have to solve it for n is equal to 3, okay. So 1, 2, 3. These are the 3 disks in hand. For 1, if there were 2 disks, I just moved disk 1 from A to B, right? So if there are 3 disks, I am assuming a scenario, let's say, what if I am able to transfer these top 2 disks from A to B? Let's say what I am doing is, I will be able to transfer them from A to B. So I have moved disk number 1 and 2 from A to B. Now 2 disks have been moved. What we are left with is disk 3. We can directly move disk 3 from A to C. So I will place disk 3 here, and I will again assume that the 2 disks that were there in rod B will be moved from B to C. Now how we are going to achieve that? If we take this assumption, okay, so if we take this assumption, I think we can solve it for any n number of disks. What I have to do, I just have to assume if there are total of n disks, first n minus 1 disk from the top, I am able to move them from rod A to B. I'll just move them. How I am going to do it? Recursion will do it for me. You don't have to worry. I am able to achieve this. I am able to move first n minus 1 disk from A to B. What I am left with is, I am left with the nth disk, the last disk. I will explicitly, now this is the task that I will have to do, I will explicitly move this disk from A to C. So, I will move disk number n from A to C. Now, the way we assumed that first n minus 1 disk will be moved from A to B, similarly we will assume that the n minus 1 disks that were there in rod B will be shifted from B to C. So, I will be able to do that. So, if this happens, I should be able to solve the problem for any n value. Now, this is what is happening is, this is recursion. So, we will use recursion here. Recursion will do this for us. So, okay, with the diagram, let's just write a function. So, the function that I am going to write is just to print the steps. So, the function that I will write will just print all the steps, and we will just the steps that I wrote actually move this one from A to B and all these steps. So, this function will write these steps for me. What input should I get? The function is, I should get three things. The source, I am just storing the source as a character, so A, B, C. So, source, then I need a helper, I will call it H, char H will have just the name for the helper, and char D is for destination. So, char S, H and D, and obviously we need the number of disks that we have to transfer. So, int n, n is the number of disks that we have to transfer. Okay. So, we are going to do it. So, the first step again that we should be concerned about is the base case. How are we going to think about base case? The simplest problem that will help us. So, the simplest problem that we have to do in order to solve Tower of Hanoi is actually, so if there is only one disk. So, if there is only one disk, that then you don't have to do then you don't have to put in any efforts. You can straight away move that disk from rod A to rod C. So, if that is the case, I should just print moving disk n from source to destination. So, we have source in character S, to we have destination in D, and that is it, and I should return because I am done with it. For n is equal to 1, I do not have to do anything else. Okay. What if n is not equal to 1? So, for any value greater than n, what we should do is, we have to assume that first n minus 1 disk will be moved from A to helper first. I will not directly move them to the destination. The first n minus 1 disk will be moved from A to helper first, and then I will work over it. So, in order to do that, I will use recursion. So, I will make a recursive call. So, how is recursion going to do it? Now, to make a recursion call, we need to tell what is the source, what is the destination, what is the helper. So, one thing I am sure about it is that I have to move n minus 1 disk, first n minus 1 disk. Okay. So, I have written that part. Now what is the source of these n minus 1 disks? Where are these n minus 1 disks actually coming from? They are coming from the original source. What is the destination of these n minus 1 disks? The final rod that I want them. So I want for my current scenario that first n minus 1 disk should be moved from A to B first. So the destination should be the helper. So okay. So let me just write here, this is source, this is helper, this is destination. What we did initially, we assumed that we have to move first n minus 1 disk from A to B. So okay, so I'll just use this portion. What I have to do is I have to move n minus 1 disk from A to B. What was A? A was the source, B was the helper. So now helper disk is my destination because I have to move to that. So helper is my destination. So if helper is my destination, then which is the helper rod that I can use? I can use, so A, so I have to start from A, put it into B, C is there, I can use C as helper. So I will use C as helper now. So the destination is my helper. So this is my helper now. So with this statement, actually with this statement I am moving, what I am trying to do is I am trying to move first n minus 1 disk from A to B. Okay, so Rohan, in line number 24, we are not doing much. What we are actually doing is that I am just assuming that I have only one disk with me. So if I have just one disk with me, what we did was we just moved that disk from our source to destination, from A to C. We just did this. So we just simply move this disk. So the statement that I am writing here is I am just writing the line that I spoke. I just moved disk number n, which is disk number 1, from the source rod to the destination rod. Now the character of source rod was A, the character of destination rod is C. So I am just moving this disk from A to C. So this is what I am doing. And after that I am writing a return here, because for one disk this is the only task that I have to do. This is the only step that I have to perform. I have already written that step, so I am done in case there is only one rod with me, one disk with me. In line number 28, what we are doing? In line number 28, okay, so let's just clear this and start again. So what our target is, what actually we want to achieve is, now we have seen for one disk how to do. I don't have one disk, I have more than one disk now with me, and I have to move all those disks from A to C, or I should write source to destination. Source is character A, destination is character C. So I have to move all these disks from source to destination. So the third rod which is there, I will use that as helper. Whatever third rod except source and destination, we have three rods, one will be source, one will be destination, I will use the third one as helper. What is helper used for? So helper is used for the intermediate steps. Okay, we will understand it in deeper once we dry run it. So this is my helper, and I am saying it is character C. I am just giving names to the rods A, B and C. The helper is B. So I am just giving names to the rods. So now the way we should proceed is, we should assume that we will be able to move first n minus 1 disks collectively. We will be able to move first n minus 1 disk from A to B, from disk A to disk B. Now in order to do so, what I have to do is I have to move first n minus 1 disk from A to B. Now for this procedure, which rod is serving as the source? Rod A is serving as the source. Which rod is serving as the destination? Rod B is serving as the destination. So one rod is source, one rod is destination. There is third rod available, which is rod C. So I'll use rod C as helper, because one is source for me, one is destination for me. There is another third rod that I can use. So that third rod is destination for me. That third rod is helper for me. So rod number A is source, rod number B is the destination, rod number C is helper for me. Exactly the line that I wrote over here, this is the code for that. So this statement is the code for the lines that I just wrote over here. What I have to do is I have to move first n minus 1, top n minus 1 disk. What is the source? Source is the original source that I have. What is the destination? Destination is the helper that I have. Then what is left? Which rod is left to use as a destination? The rod which is supposed to be the final destination, I will use that rod temporarily as a helper for me. Okay, so this is just a step. So Suman is asking, why are we using D as, or the destination as helper? See, again I said, so the whole step that we are going to follow is move first n minus 1 strings from A to B, move nth disk from A to C directly, and then move n minus 1 disks from B to C. Now why we are following this step? Because we have to transfer all the disks from A to C as it is. So what we are doing is we are assuming, recursion mein the two questions we saw, we were just assuming that smaller problem will be solved for us. So if you have to place n disks, the smaller problem would be placing n minus 1 disk. I'll assume the smaller problem will be solved for me. So the smaller problem is moving n minus 1 disk from one rod to the other. That's it. So what I'm doing is I'm assuming the smaller problem over here will be solved for me. Moving first n minus 1 disk from A to B. This is the step. Now in order to conduct that step, A is the source, B is the destination. The third rod that I have, I'll use that as helper. So okay, so I am just writing this, move n minus 1 from A to B. This step that I have written over here, this is the code following for that step. So the code for the step is this. What was the task? The task was to move n minus 1 disks. I have to move them from A to B. A is the source, so this is the source. The destination is B, the helper disk that I had. So this is my destination. The third disk, that is D, the third rod, sorry, that is D, is left. So I'll use that as helper for my intermediate steps. So this is the task that I can assume. First n minus 1 disks are moved from source to helper. Okay. So after this task, the next step in line is move the last disk from A to C. So I'll now just write the code to move the last disk, that is the same statement that we wrote over here. I'll just use the same statement. I have to move nth disk explicitly, so I am writing this step to move nth disk from A to C, from source to destination. So I am using this nth disk from A to C. We have moved nth disk. So nth disk is the only disk which is placed at its finally correct position. Now what we are left is n minus 1 disk are still waiting at rod B to be transferred to C. So now I have to transfer all those n minus 1 disks that are there in B to C. So in order to do that, Tower of Hanoi, What is the source of these n minus 1 disks are now? So we already transferred them to helper, so they are there at the helper. What is the destination for them? Destination for them is the final destination rod, we have to put it at them. What is the third rod we are left with? We are left with the source rod, we are not using it correctly, so we will use the source rod as helper. Okay, so these are the steps. Don't worry, we will understand it once we run it. We will see how are things working. So please don't worry much. You don't have to remember any statements. See, what you have to do is you have to understand the problem. These statements are pretty simple once you understand it. The purpose of this webinar is to give you a hold of recursion and not to make you cram things up. So you don't have to learn things or do that. You just have to understand it. And this B, C are just the titles. These are just the names of the rod. Okay, so let me just do one thing. These characters might confuse you. So this is A. I'll just rename them as we have them, A, B and C. Let's just rename them. I hope that will give you a clarity of what we are trying to achieve. If there is only one rod, I simply have to move it from A to C. These A, B, C are just the titles. I am repeating again. If there are more than one rod, what I have to do is I will first transfer n minus 1 rods from A to B. The third rod, that is C, is available for me as a helper. Next, what I have to do is I will move last rod okay. So let's just comment these. And call Tower of Hanoi here. What we are supposed to pass is names of the disk. So first is character A, next is character B, next is character C, and let's just run it for n is equal to 2 for now. Okay, let's just run it for n is equal to 2. Okay, so let me just clear this. Okay, so we just let's just figure out what the error is. Okay, I just missed that at line number 38. So there's just a spelling mistake. Let me just correct that. Okay. Okay, let us compile our code and okay. So the steps if I have to transfer 2 disks are, if I have 2 disks with me, so what we are doing is, this is A, this is B, this is C. We are moving disk 1 from A to B, this is disk 1, this is 2. So, we will move 1 from A to B if I have, and then I will move 2 from A to C, directly I will place it over there, disk number 2. And when I am just left with 1 disk, so I will move 1 from A to C. This is the step. So, in this n is 2. So, this is the first step where we assumed that we will be able to move n minus 1 disk from A to B. So, this was our first step. Next that we did, if I just go back there, next that we did was we ourselves moved the last disk. So, this was the step where we ourselves moved the last disk from A to C, and then I assume that remaining n minus 1 disk will be transferred from B to C. So, this was the step for 2 disks. Let's just run it for 3 now, so that we have a better understanding. So, n is 3 this time. I have to transfer 3 rods from A to C. Okay. So, these are the steps if I have to move 3 rods from A to C. Let's just say these are the disks that I have. Rod number A, B, C, and disk 1, 2, 3. Okay. So, while writing code, what we were doing was, so we were assuming that n minus 1 disk will be moved, this statement, right, n minus 1 disk, that means first 2 disks will be moved from A to B. So, that is the problem that recursion will solve. Obviously, you have to follow the constraints, you can only move 1 disk at a time. So, you will have to follow the steps to do that. What are those steps that recursion is telling me? So, these 3 are basically the steps that I will follow. What I should do is, I should move disk 1, this disk, from A to C. I will place 1 over here. Next step is move disk 2 from A to B. So, move disk 2 here. Next is move disk 1 back from C to B. So, I will place disk 1 here. Now, at this stage, I have reached to a situation where which was my assumption that first 2 disks will be transferred from A to C, which is there, right, which is true, which is done by recursion. So, this is actually achieved. So, n minus 1 disks have been moved from A to B. What is left is, the task for us is to explicitly move disk 3 from A to C. I will move the third disk from A to C. So, let's just clear this. I will just move the third disk, disk 3 from A to C. This 3 is there. Now, we are at a state. Which state we are at? We are at this state. We have moved first n minus 1 disks from A to B. We have moved the last disk from A to C. Now, we have to bring these n minus 1 disk from B to C now. That was what the statement was doing. This statement was to move the n minus 1 disk from B to C now. So, in order to do that, what are the steps that we should follow? These 3 steps are basically the steps that we should follow. What we should do is, we should move disk 1, which is this, to, this is empty now, to A. Now, we should move disk 2 to C, and finally bring back disk 1 from A to C. These are basically what the steps are doing for us. So, Atif, it can be, C is just a helper, so you don't have to think about that. So, these were the steps that we were doing. What was recursion? What we were not worrying about? We were not worrying about these steps. Recursion was doing this for us. Recursion was moving these n-1 disks. Obviously, you have to perform all those steps one by one, but we don't have to take its tension. And that's what is actually the best part of recursion. That's what is recursion is important for us, because recursion makes it easy for us to think about problems. So, initially, the two simple problems that we actually did iteratively, that we did recursively, were pretty simple problems, and that can be done iteratively as well. We did initially simple problems just because to get an understanding of recursion, so that we can move ahead with and solve tougher problems around recursion. See, first we should understand recursion and then we can proceed towards harder problem. So that was the goal. We initially did these simple problems because we should achieve and understand recursion first and then move on to solving different problems around it. So if I have to solve a problem like Tower of Hanoi, now thinking this way is very, very easy for me. So if I have to think it this way, it becomes quite easy for me, and I am just assuming that n-1 disk will be moved from A to B and then later from B to C. I don't have to think about the steps how those n-1 disks will be moved. So for me as a developer, it is way easier to think of writing code this way. Comparatively, if I have to write a iterative approach, it will take me a lot more time. So it is easier for me to visualize things recursively, assume that n-1 job will be done, and I just have to perform one simple step. That ways it is quite easy for us. Okay. So we just did a try run for n is equal to 3. Similarly, for so since some of you are asking to try run, let's quickly do it for n is equal to 4 as well. Let's go back to code, edit there. Okay, so these are the steps that you have to perform if you have to move 4 disks from 1 to C. If you look up to the stage over here, now these steps are to actually move 3 disks from A to B. So these are the steps that I am performing to move 3 disks from A to B. What we have to do is move the 4th disk from A to C. Now all those top 3 disks were there with us. Now they are there with us at B. We just have to bring them back to C. So these are the steps to move 3 disks from B to C now. This is the procedure that is being followed. So in previous dry run we understood, right, how things work for 3 disks. So we are just using that and reaching out to solution for 4 disks. Similarly, we will just use that and move up and solve it for different values of n. So I know that for 3 my code is working fine. Similarly for 4 it will work fine, because for 3 it is working fine, and for 5 and so on. So these were the steps that you have to solve for Tower of Hanoi problem. Okay, so for if you have to solve a Tower of Hanoi problem for n disks, then the number of steps that we actually perform r 2 to the power of n minus 1. So some of you were asking for time complexity analysis of tower of Hanoi problem. So we have some time with us. So let's quickly go through the time complexity analysis. So okay, so let me just go back to code for a quick time complexity analysis. So this was our Tower of Hanoi code. In last webinar, we did time complexity and we learned time complexity analysis of different algorithms. So for recursive algorithms, we think of it in a different manner. So the recursive equation that I have to write for this problem would be that in order to solve the whole problem, that is Tower of Hanoi of moving n disk, what I need to do is I need to solve a problem of size n minus 1 first, that is moving disk from A to B. So I have to solve a problem of size n minus 1 first, and then it will take some time to transfer the last disk from A to C, and then I have to again solve a problem of size n minus 1. So that means I have to solve two problems of size, sorry, that should be n minus 1. I have to solve two problems of size n minus 1. So that is 2t n minus 1 plus some constant k. Basically, this is the problem that I have to solve. So this is the recursive equation for the problem. I think it's easier to understand this way. So Tower of Hanoi n, in order to solve Tower of Hanoi n, I was first making a call to solve the Tower of Hanoi problem for n minus 1 disk, move them from A to B, and I had to make another call to move those n minus 1 disks from B to C. So I had to make solve two problems of size n minus 1 in order to do that. Similarly, to solve problem of size n minus 1, I have to solve four problems of size n minus 2. So if this continues for every step, and this will continue till the point I am left with only one disk. So the total time taken by the function to solve will be proportional to the number of function calls that I am making. So here I am making just one function call, so this is one. Then in next line I am actually making two function calls. In every function call, if you see this function, I am doing some constant amount of work besides making two function calls. So I am making two function calls and doing some constant work, that is moving one disk. So next time I am making two function calls, next time I am making four function calls, next time 2 to the power 3, 2 to the power 4, and it will continue. Till 2 to the power n. So this will continue so on. So if this is a GP series, right? If you just solve this GP series, it will come out to be this, power n minus 1. So it will come out to be this. This was still 2 to the power of n minus 1. So this GP series will actually, if you solve it, the formula is a into r to the power n minus 1 by r minus 1. So r is 2 here, a is 1. So if I will just So this is the number of function calls that I am doing is this. If in every function call I assume that it takes some constant time k, then the total time taken by the algorithm to run is 2 to the power n minus 1 into k. So which means the complexity of this function is big O to the power 2 to the power n. So this is what is the time complexity of the Tower of Hanoi problem that we did. I'll just quickly repeat this time complexity part in case it is not clear to some of you. See, the total time taken, so what we are doing in order to solve the Tower of Hanoi problem, we have to solve a Tower of Hanoi problem of size n. We are first moving n minus 1 disk from A to B, and we are then moving one disk from A to C, and the n minus 1 disks which are there at B, we are moving it back to C. So that means we have to solve two problems of size n minus 1. So if I have to write the recursive equation, then the recursive equation will be like this. We can solve recursive equation, we can compute complexity via solving recursive equation as well. What I am doing is I am solving complexity, writing it pictorially so that it might be easier to understand. So n is basically the problem that I have to solve. In order to solve this, I made two calls of size n minus 1. So one call here, one call here. Similarly, for n minus 1, I will make two n minus 2 calls, these, and similarly other n minus 2 calls here. And this procedure will continue till only one disk is left. So the total time taken by the algorithm will be proportional to the number of calls that I am making. So let's count how many calls I will make for size n. First step, I made just one call. At second step, there were two function calls in total. At next step, there were 4 function calls, then 2 to the power 3, 2 to the power 4. At last step, there are 2 to the power n minus 1 function calls in total. So now I am there with the GP series. If you solve GP series using this formula, you will get this. These are total number of function calls that is taking place. If one function call takes k time, then this is the total time. So now the dominating function is 2 to the power n. So the time complexity of this Tower of Hanoi problem is 2 to the power of n. So exponential, the Tower of Hanoi problem that we solved has exponential time complexity. I hope this part is clear to all, and with this we will come to the end of the webinar session. I hope you guys have liked it and have understood about recursion. So there is a small test at the end of the session that you guys can do. I'll just put up the link for the test here. So this is the link for the test. You guys can take this test and understand it. Okay. So Piyush is asking what are the advantages of using recursion. So Piyush, recursion actually helps us, again as I said, it helps us think and solve problem relatively easier, better. I will take less time writing a recursive code as compared to writing a iterative code and understanding through it. So it helps us understand stuff better, and we are able to write code faster. The code turns out to be cleaner, smaller. So that's why basically recursion is quite popular. So this k basically here it just specifies the constant time that I am taking in one function call. So in total number of function calls, the constant time would be 2 to the power of n minus 1 into k. Okay. So I have put up the link for the test. You guys can take that test. Also, we have started with the registrations. We have already started with the registrations of our summer batches. So if you guys are interested for joining us for the summer batches, which are foundation courses and advanced courses, So you guys can join us. We also have a scholarship cum admission test for you guys, those who are interested. I am putting up the link for the test in the chat. You guys can go through the link there and register for the scholarship and admission test if you want. You will be getting scholarships based on your performance in the test. So, okay. So, I hope you guys enjoyed webinars and our webinar. So, thank you for it. Okay, thank you.